So far in this class, we've talked about motion. We've talked about what we mean by position, velocity, acceleration, and how these are related. We know acceleration, if an object is accelerating, its velocity is changing, which could mean speeding up or slowing down or changing direction. Velocity, of course, is how fast the object is traveling and in what direction it is headed. Position is where the object is at any given moment in time. So far we've just talked about how we can describe motion, how acceleration and velocity can determine where an object ends up or where it is at a specific moment. This next section we're getting into is going to talk about what causes motion. Okay, so what gives an object velocity? What causes an object to accelerate? So this concept is called dynamics. Just the term dynamics means relating the cause of motion to the actual components of motion in and of itself. Ultimately, the cause of motion is a net force. So this video is going to introduce the concept of forces. So introduction to forces. Now, the concept of force is probably not new to any of us. A force is any type of push or pull. There's many ways to push or pull, and we're going to talk about different types of forces and how to look at how forces affect motion. A couple of things first. When we talk about a force, we need an object that's going to feel the force. I put feel in quotes because, of course, a box cannot feel anything. But in terms of an object to feel or experience the force. So when we talk about the object, say I have a box and I pushing on the box. The box itself is the object that I am talking about experiencing the force. So anytime we talk about force, there needs to be some sort of object that is experiencing or feeling that force. But something has to cause the force or create. Our author calls this the acting agent. So in this particular example, I would be the acting agent because I am the one pushing on the box. So I'm causing or creating the force. When we talk about Newton's laws, we'll find also that we can swap where I become the object and the box becomes the acting agent. Meaning, as I push on the box, I too feel a push against my hand from the box. And so you may have heard of Newton's third law before, where for every action there's an equal and opposite reaction. That's what we mean. As I push on the box also is exerting a force on me, and I feel that, just like the box is experiencing the force that I'm applying. That's one reason I call this feeling the force, even though a box technically can't feel it, of course, but just to describe kind of what's going on between the two, object versus acting agent. So forces, we have two categories of forces that we will talk about this semester. One category is called contact forces. A great example was what I just said. I put my hand out, I put my hand on the box, my hand is physically in contact with the box, and I push. So me pushing on the box is an example of a contact force. What we mean by contact force is there's an actual physical contact between the object that is experiencing the force and the acting agent that is causing the force. The acting agent does not have to be a human. For example, I could have a box and tie a rope around it. A rope. Now, granted, I would have to grab one end of the rope, but the rope itself is what would be pulling on the box. So a rope pulling, we would call that a force of tension. So the acting agent would be the rope. We would essentially boil this down to call it a force of tension. So tension is a type of contact force. When we think about a rocket, if I have a rocket, and yes, please forgive my drawing. I'm not the best artist. So if we get a rocket, I guess it doesn't need to be an initial, but a rocket moving upwards, the gases getting pushed downwards creates an upward thrust force. So that's an F to mean force, and the subscript, I'm just writing thrust out right now. Thrust would be considered a contact force as well, because those gases are physically in contact with the rocket. So that would be another example of a contact force. A force between an object sitting on a surface. So if we go back to the box example, if the box is sitting on the floor, which of course typically it needs to be sitting somewhere, the floor would push upwards on it. The floor pushing up would be a contact force. We call this a normal force, not because there's anything normal about it, but because of the definition of what's called a normal vector. When you get into vector calculus, there's a definition of a normal vector such that the angle between the vector and the surface is exactly 90 degrees. So the floor is pushing straight up. The floor itself is horizontal. So the angle between the floor and the push upwards of the floor is 90 degrees. If we had an incline and our box was on an incline, we would draw this normal force so that the angle between these two is 90 degrees. Any surface that is pushing on an object, we call this a normal force because the direction of that push is always perpendicular to the surface. So that name normal just comes because of that perpendicular direction. That's where normal means, is perpendicular to the surface. If I was in the classroom and I have the whiteboard and I put up the eraser to erase the whiteboard would push outwards on the eraser. We would call that a normal force. The whiteboard is a surface. The force the eraser would experience from the whiteboard would be perpendicularly outwards. And so any type of surface pushing on an object, the direction is always perpendicular. So the direction of this force is always perpendicular to the surface. And we call this force the normal force. The normal just means perpendicular to. So anything, any type of object on a surface will experience a normal force. We've been ignoring air resistance and drag, but that would be technically a contact force as well. We still will, for the most part, ignore it for the same reason, because of the complexity of the math. We will talk briefly about it in chapter 6, but for now, just know that it is a contact force because some sort of object is moving through the air. So it technically is a contact force. Later we'll talk about springs. So if I have a spring, excuse me, and I hang a mass from it, I know the spring will stretch out. And so this mass will feel or experience a force from that spring. Now, the reason it stretches out, though, is the mass is attracted to the earth. The earth itself is pulling on the mass, trying to pull towards the center of the earth. That we call the force of gravity. Force of gravity, though, is not a contact force. I mean, this spring, this mass on the spring is a good example. The mass is not physically in contact with the earth. We know if we have a ball in our hand and we let go, the ball is going to fall towards the earth. The reason the ball falls towards the earth is because of the force of gravity. But again, that force is there whether there is physical contact between the earth and the object or not. So this is the second category of force. So up here mentioned there's two categories. One is a contact force, meaning there's actual physical contact between the object and the acting agent. Gravity falls in a category called field forces. You may have heard the terminology action at a distance. So another example that you would be familiar with would be magnets. Magnets can be fun to play with. If you have the sides that repel each other, facing each other, trying to push them together, of course, can be entertaining. The magnets themselves do not need to physically be in contact with each other. This is action at a distance. We call this a field force. So by field, we just simply mean these forces are existing. There's attraction and potentially repulsion simply because the objects are near each other. So magnets fall in that category. Electricity would fall in that category as well. Our main use and our main force, of course, is going to be the force of gravity. We cannot get rid of the force of gravity for any objects on or near the earth. Our author talks about this in terms of weight as well. When we talk about the weight of an object or the weight of a person, we are essentially talking about how hard the earth is pulling on the object. So the force of gravity, I'm going to write this as F sub g. It depends upon the mass of the object and the acceleration due to gravity. So again, little g from previous sections means 9.8 meters per second squared. We do know what point the actual acceleration points downwards. So the force of gravity points down, meaning towards the center of the earth. So we write the force of gravity as just m times g. What we mean by mass SI units is measured in kilograms. So kg. Mass is representative of the molecules, the amount of stuff that make up the object. Any given object has a set mass. So if I have a 2 kilogram mass here on Earth, and I'm an astronaut and I travel to the moon, it would still be 2 kilograms on the moon. It would be 2 kilograms on Mars. It would be 2 kilograms in the middle of outer space, nowhere near any planet or star or sun. Mass is completely and totally related to the number of molecules making up that object. The actual weight is the force of gravity on Earth, mg, where g is 9.8. If we went to the moon with this example, the weight would be mg, but g on the moon is approximately 1/6 of 9.8, which is not a value you need to remember. We just need to recognize that the acceleration due to gravity is completely dependent on where we're talking about. So here, of course, we're going to be talking about objects on the Earth, because that's where we live. And so g, we will continue to use 9.8. But we do want to make that distinction between mass and the force of gravity or weight, so that we are not interchanging them and confusing them. Magnets, electricity are both types of field forces, in that we can have a magnetic attraction or repulsion, or electric attraction or repulsion based on the, like electricity, it's going to be because protons and electrons are attracting each other, because opposite charges attract, but they do not need to physically be in contact with each other. And so that's why we call it a field force. They attract each other simply because they're somewhere in a general vicinity close to each other. All right, so as we are moving through this section, our main field force, of course, is gravity, the force of gravity. All the other forces are going to be contact forces, meaning there's some sort of physical contact between an object and its acting agent, and a push or pull occurs because of that. When it comes to analyzing motion, we will need to be able to account for all the forces acting on an object. And so we're going to go through how to look for those forces, how to represent those forces in what we call a free body diagram. And then we'll build on that to write equations that will allow us to relate forces to acceleration and in turn the motion of the objects.